Okay, so welcome to another lecture of probability and statistics. It's really cold, I should say, and it's early, but here we are. So this is lecture number 8, and today we finish what we started last week, and we add the confidence interval. So we will be talking about a second method to estimate our parameters of the distribution that we don't know. And we will add the confidence intervals, which are a measurement of how confident, how good our estimators are. Okay? So this is what we're going to do today. So last week, I think we have a similar slide, if not the same, that the problem is that you have data and you don't know what distribution comes from. And even if you know the distribution where it comes from, you don't know the parameters of the distribution, right? So usually you want to estimate your mean or your mu and your standard deviation or variance, okay? And for that, we saw that there is one method that we spend a lot of time deriving this equation of the moments. And using this method for the moment, we have one way to estimate this. Today we're going to see another method that's called the maximum likelihood expectation method, and also aiming at the same idea but from a different approach. And we will see how we can estimate how confident we are in this estimation. So basically this maximum likelihood estimation is we try to maximize the probability that we are correct, let's say, at estimating the parameters. And we can start with a set of observations, as always, so you will have some data. And then, since we don't know the probability, our estimation of the probability is going to be just our the probability of occurrence, right? The number of occurrence over the total number of samples that you have. So, to motivate this, let's just put it in an example here. Let's say that we have a box again, and we have balls inside. And some balls are white, and some balls are blue. And we start drawing, and let's say that we want to know the probability of getting a blue ball out of this box. So what you will do is take samples, right? You will take samples of balls, and you will watch it and say, okay, this is blue, this is white, and whatever. And then depending on the number of blue and white that you get, you calculate your probability. That's what you will do. So let's say that you draw 10 balls, and let's say that the first is, let's see that this is blue, it's red, but it's blue. Imagine that it's a field ball. And then the next ones are all white. So if you calculate the probability, then it's going to be 1 over 10, right? And then you will say, well, there is a 10% of chances of getting a blue one, right? So this is nothing that our P estimation, which is K over the number of drawings, and this will be our estimation of P, of the probability. Let's say that you repeat the experiment now, and now you get, I don't know, at some point 2 blue. You always replace, right? You take one and you replace it. So you could get 2, you could get 3, I don't know, depending on the amount of blue that you have there. So let's say that the next time is you have 2, the next time maybe you get 3, maybe you get 4, but that will be really rare, they start to be rare. And also it will be started to be a little maybe rare that you get 1 only. So you will oscillate in between 0.1 and 0.3 or 4 in this case, let's say. So then you can count how many times you get a 0.1, how many times you get a 0.2, and so on. And then you can construct this curve that you see here of the probability of getting your probability. Okay? So how likelihood is to get some kind of probability. And there's going to be a peak. In this case, hopefully around 0.2, because most of the time, hopefully, you will get, if you draw enough, if you repeat this experiment many times, the 0.2 should pop up more often than the other. So there's going to be this peak. And then calculating this peak is the idea of the method of maximum likelihood estimation. Okay, so you will estimate the likelihood of getting some probability. And in this case, we estimate the probability, but you can estimate your lambda, the parameters of the gamma distribution, and the beta, and the alpha, the mu, the standard deviation, so on and so on. So the idea will be then repeating an experiment many times, observe your calculation. So you could repeat this, for example, every time that you have, for example, a continuous variable, you read it out, and then you repeat 10 times, and you calculate the mean. And that's going to be one mean. Then you repeat it and have another mean, and then you build your distribution, and then you calculate the maximum of that. Okay? So it's always about calculating a maximum of a function that we create, but experimenting with your data. That's pretty much it. And as you know, once you have built a function, then if you calculate the derivative of the function and you equal to 0, you can find the maximum. And the value that makes you the maximum is the value, the estimate of your distribution. Okay? So we're going to go through this for many things. So basically, the idea is you have what is called the likelihood function, which is a function that maps your data into the probability of having this data given an estimated parameter. Okay? On the other way, so this is this is not the likelihood function. The likelihood function is what I say that is here. So given the data that you have, the estimated parameter, right? From the parameters from the whole universe of parameters, you map it to the probability of getting certain parameter given your data. This is what you will usually get as a probability function. Sorry, this is the probability function. This is the likelihood function. So that's what we're going to do. Then, like I say, if you calculate the maximum, you will get the maximum likelihood. That's the first name. And then the estimation is because you are estimating this, because you will be drawing not infinite number of points, but some number of points. And then what we're going to do is to take this maximum and equal it to 0. You will see. So how you build your likelihood function. So this is the critical part in all the examples. So the critical part is for each of these realization that we have here, you can calculate your likelihood, right? So this is 0.1, 0.2, 0.3. And we assume that they're independent. Once you take it 10, the next 10 are going to be independent to the rest. So we can multiply them, one each other, right? So you can multiply this sub-likelihood function, let's call it, together to build the total likelihood itself, right? And then your likelihood function is just a multiplication of the many times that you have to do this experiment, okay? And then you take the likelihood, you divide it, you differentiate it with respect to the parameter that you want to find, and you equal to 0 to find the maximum. All right? So with that, we can go to our first application, let's say, or example, that is a binomial distribution. So for the binomial distribution, we know that the formula of the probability function or density function is this one, right? And let's say that we want to estimate what is the parameter that we can estimate in the binomial distribution. It's a p, right? The rest is given. X and k are going to, x and n will be, n is the number of drawing, x is the that you want to find, right? So let's try to estimate p from here. So let's say that we are interested on the event A to occur. Remember, it's A or complement of A. It's two options only. And let's say that from the many times that we draw this, k times result in an A, and n minus k result in an A complement. Okay, normal stuff. So you can put it in a function here as the probability to be k times 1 minus probability to the n minus k. Why there is no combination here? Because k in this case is fixed. There's no need of rearrangement here, okay? So you will have to repeat this, as we saw at the beginning, many times, right? So we repeat this n times, right? And then it's just a multiplication of what you calculate for each of the time each other. So for K1, for K2, K3, and so forth, so forth. And then you just multiply. And voila, that is your likelihood function. So now we have our likelihood function. Now we have to find the peak, the maximum, right? So here is split it in another way. So one trick that we're going to apply before we calculate the maximum is to take the natural logarithm of this function. We do that because it's much easier to deal than for the derivative, because the properties of the natural logarithm are very useful in this case when you have things to the power of something, or when you have an exponential function, for example, right? So what we're going to do is we take just the logarithm, the natural logarithm of a function, and if you do that, then you can split it here, right? Logarithm of p to the k plus logarithm of 1 minus p to the nk, right? Just enter the logarithm inside there. And then if you remember the properties of logarithm or the natural logarithm, you will have that the k go down, right? When you have logarithm of p to the k goes down and multiply logarithm of p. And this is where it starts to be useful to do this. One thing before I forget, calculating the maximum of the function and the maximum of the logarithm of the function will give you the exact same peak. That's why we can do this. It's just because it works out. If not, we will be calculating something that is not correct. So we do the same for n minus k here. We put it back, we take it down, let's say, and then we multiply by logarithm of 1 over k. So with that, now it's much easier to differentiate with respect to p, because this is what we want to find. And then if you take the derivative of the function, so logarithm of p of the variable is 1 over the variable. Okay? Again, if you remember that, times k, because k is a constant. The same here is 1 minus p, so 1 minus 3 goes in the denominator times n minus k minus 1, because when it's in this construct, you have to change the sign. This is, again, properties of the logarithm. And then at the end, you end up with this. And now this is the differentiate, the derivative of the function. We have to equal this function to 0. And this is what I do here. And if you solve this, you find nothing but the probability is k over n, which is no surprise because this is what the polynomial distribution is, right? So, but this is just an example and application of how we can use this maximum likelihood estimation, okay? I hope this is clear. This is simple. So this is what I wanted to show you before. Even if you have an example here that you have n equal to 120 samples and you have a realization of 6 that actually appear to be A, then the probability is k over n, right? Nothing new, but this is the important thing. This is the likelihood that you have built with the binomial distribution, and this is the logarithm. Likelihood, logarithm. You can see that even the shape is different, the peak is exactly at the same point. So you can trust that if you take the logarithm of the likelihood function, it will give you the same peak when you need it. All right, so let's go to another distribution, as we always walk over different distribution. So if we have a Poisson distribution, what do we want to estimate? We want to estimate mu, right? Mu is our variable that defines the Poisson distribution. And so we have to construct our likelihood function here. So what we do is, again, is a multiplication of the different Poisson distribution for different values. And this is nothing but multiplying our function n times. And then if you group them, you will have that this part can be grouped here, and the exponential part can be grouped here. And these guys are going to be just mu to the sum of the x over multiplication of factorials. And these guys are going to be just a to the n times mu, because it's always mu in the power. Okay? So this is our likelihood function now. What we have to do, we have to take the logarithm again. natural logarithm or likelihood function is natural logarithm or our result here. And what we do is, again, the multiplication, the logarithm of the multiplication is equal to the sum of the logarithm of each part of the multiplication, right? Again, properties of the natural logarithm, and this is what is so good to use the logarithm. And then if you have a fraction, it's going to be the subtraction of them, of the numerator and denominator, and with the numerator in the positive and the denominator in the negative part, always calculating the logarithm, right? And then the logarithm of an exponential is whatever is in the exponent, right? Because they cancel each other. So it's nu here. So we are getting better. Again, if you have logarithm of the variable to something, you put down the something and you multiply by the logarithm of the variable, right? And then you will have this remain the same because there's nothing that you can do, and this remain the same because there's nothing to do. So this is our likelihood function that we have to differentiate with respect to mu and equal to 0. So that's what we do here. We differentiate with respect to the variable that we want you to find out, or the parameter. And then if you see the previous one, the derivative of this with respect to mu is nothing but this becomes 1 over mu, right? And this is a constant, so it's there. If you take the derivative of this part, there is no mu here, so it gets 0, nothing there. And the derivative of this is just n, because it's a constant time mu, okay? So this is what we get here. And this function now we have to equal to 0 to find the peak again. And this is what I do here. And if you solve for that, what do you get? You get the famous arithmetic mean. Wow, this is horrible. Go. Let's put it back. I think the computer is a little bit sleepy. There you go. So 1 over n, right? Our famous average, arithmetic average, which is what you should expect from the Poisson distribution. So that's how we estimate that. So far, one variable sounds good. So this here an example. They say we have our famous decay, that we always, atoms that decay over time is a longer process that happens with a very low probability. You can already, I hope at this time, if I ask you in the exam, give me an example of Poisson distribution, you will know what to say. So we always give it this example because it's really, really Poisson distributed. So then you will have our function, right? And then you want you to know your mu. So you will have data, and the data usually will be collected in this way. So how you can identify your mu? So you will have the number, let's say, of decays that you can measure in some interval of time, whatever the time is. So let's say that in 4 intervals you get only 0, nothing. In 16 intervals of time you get 1 decay. In an interval of 31 you get 2, and so on and so on. So then you will have for 0 decays in 0 intervals, well, for saying something. You will have 0 of 0, you will have 16 times 1, so 16. 62 or 31 times 2. So this will be like plotting to make it more clear, maybe. Now I'm realizing. If you have your values here, this will be 0 and this will be 10. So you will have something like 0, and then it will be going like this, and then something like that, right? So you will have your distribution here of data, and you will want to find the mu on this. So how you do it is just sum the number of occurrence, which is multiplying the number of decay times the interval, and you divide it by the amount of observation that you have, 200, and then that's your mu. Nothing really crazy here or new. It's just to apply our estimation of the mu. So this is not the true mu, right? But it's our estimation from the population. This is just 10 samples that you have. No, 10 no, but yeah, 200 samples, sorry. So 200 times you have drawn this from infinite. So it's just an estimation. Then you will have different, this is just to show you how the Poisson, the probability, it will look for different mu. Nothing important here. Okay, so more interesting or more complicated if with the normal distribution. With the normal distribution, you not only want to estimate mu, but you want to estimate your variance. These are the two parameters that define the normal distribution, if you remember. And how we do this? Well, again, we have to construct a likelihood function. And how we do that? We just do normal distribution of each of our, anytime that we draw some samples, and we multiply each other. So it's basically repeating this equation n times, right? And again, there are some constants and some things that are variables, so you can group this part here n times, and you can group the exponential part also n times. So it will be, these are all the same values, so it will be just to the power of n, because you are multiplying them together. And here you have to sum the exponentials, right? The exponent of the function. So here you sum it here. And to make it a little bit more readable, this part here, we call it alpha. So alpha is just the thing between the brackets. In that way, it makes the likelihood function a little bit more treatable or more malleable, right? So we have the likelihood. Now what we do? Logarithm. Perfect. Wonderful. Yeah, we are good. Very good. So logarithm. Take the logarithm. If we take the logarithm, again, multiplication is equal to a sum in the logarithm. So we can break it in two. Logarithm of of a fraction is the numerator minus the denominator. Numerator logarithm 1, denominator logarithm of the whole thing here. And then logarithm of the exponential, they cancel each other, you only get the exponent. Good? You see how useful is the logarithm here. Logarithm 1 is 0, right? Then you get minus n time, because you have your potentiation here, your power, you coming down to here, times whatever is in between the bracket, minus this stay the same. Then you have to do the logarithm of here, so minus logarithm of this part, minus n comes also here, logarithm of the standard deviation, okay? And the other part stay the same. And finally, we replace alpha from what we call it, which was this summation, this big summation of each values minus the mu. And if you replace alpha here, ta-da, you have your likelihood function. This is what we want to differentiate equal to 0. With respect to what we're going to differentiate in this case? We're going to have to do two times, right? You have to differentiate with respect to mu and to respect to the variance, because they are the two things that we want to calculate. And this is what you do. If you differentiate with respect to mu, you get this. If you differentiate with respect to the standard deviation, you get this. And these two guys have to be equal to 0. The good thing is that we have two equations, and we have two unknowns, two variables. So this should be a solvable set of equations, right? So we can start with the first one, because it looks easy, because if you multiply by the standard deviation or the variance, the estimated, but you see that the hat is in here because it's now the estimated, right? Because when we equal to 0 is the maximum, the hat means always estimation. So since we have the variance in both sides, we can multiply by the variance, and then we get rid of the variance already. So we can do that, and then we'll have just this part equal to 0. We enter the summation here, and this is nothing by n times mu estimated over this. And then if you solve for mu, you get again that the mu is the arithmetic mean, as in the Poisson distribution. So now we know that mu is the arithmetic mean, so we can replace mu by the arithmetic mean here in the second equation. And if you do that, you solve for the variance, and you get the equation of the variance that you have learned before. Remember, I don't know if you remember, I think it's like 3 or 4 weeks ago, we talked about this, that this, because how was the defining the variance at the beginning? It was the summation of x sub e minus mu squared times the probability of x, remember? So we say that if we don't know px, if we know the distribution, we have to come to this function. It was like magically say in that respect, because we assume that they are all with the probability of 1 over n. Well, now you have a proof of that, why we come with the variance, okay? Because it's the best estimator of the mean in the normal distribution, okay? This is the best. And I say the best, not because I am fanatic of this equation, but because it's unbiased. This is, it's not the best because it's biased, sorry. The equation here have one problem. Again, I don't know if you remember the low or large numbers that we say that in the infinite they will stabilize at some point to the mu, right? But at the beginning there was some jitter, that they will make some noise, right? This is like here. There will be, if you don't do anything, it will have something like this. So this is the estimated variance. At the beginning, for some sample until here, let's say, you will have some problem with that. So we have to correct that. That is because it's biased, this estimator. And the way that Bessel found it out is just by, instead of doing 1 over n, you just do 1 over n minus 1. And this incorporate here a factor that is n over n times n over n minus 1 times the estimated variance, which if n becomes very big, then this 1 is not important anymore, and you just get the same. The estimated will be your estimated variance. But if n is smaller, there's going to be some factor there that will actually correct this, and you will get the blue line now. So remember, the mean is the true, the mean arithmetic mean is the true mu of the normal distribution, but the variance is a biased estimator, and we need to correct for that. Okay? Good. An example, of course, of normal distribution. Let's say that we draw some data from whatever it is, 10 samples, and these are measures, 200 and something of each measure. And then we will have 10 samples. These are measures. This is the difference between the measure and the mean. You can see that it's easy to calculate the mean, because if you sum up all the measures, 2,500 divided by 10 is 250. This is our mean. And if you subtract 248 to 250, you get minus 2. 250 is exactly the mean, 0, and so on, right? So this is the difference between, I can do it here. Right? 250. So this is what we are doing here. Then you have to square to calculate your variance. These are the values squared. So 2 minus 2 to square it is 4, and so on and so forth. All right? I think I did the calculation here. Yeah, there you go. So how you calculate the variance? You just have to sum all these that you have calculated here and divide it by 10. If you want to have your bias estimator, that gives you 5.2. If you want to have an unbiased estimator of the variance, you subtract 1, and then this will be a more correct way, because we have only 10 samples So when I say we have only 10 samples, watch out, because it doesn't mean that there is a specific number that we can say, well, now we are safe and we don't have to correct. To be honest, I think we can always use this correction, because in the worst case, these two values will be very similar. So to be safe, you may want to just subtract 1 every time. If you have 100,000 samples and you subtract 1, it's not going to change anything. You can already sense that, right? So I would suggest you always subtract 1. So these are estimators of the normal distribution of that particular case. All right, so I hope we are by now very clear how we can use two methods to estimate our parameters of distribution. Now we have to learn how we measure how good we are in estimating these parameters. And we do that by using what is called confidence intervals. So we will define an interval where we are confident with some percentage of confidence, okay, that our estimator is true. How we do this? We have to define the borders of a confidence interval, right? So we will have our estimator, and we also going to estimate our left border and your right border, let's say, of this. So this is coming like if you have your distribution and you have estimated that this is your mu. Well, there are going to be some borders that are going to define pretty much how that our mean is going to be around this border. We don't know exactly where it's going to be, but it's going to be in some place here. That's the best that we can say. And there is a magic number that I'm going to explain it later, how we come with this magic number. But if we want to be 95% confident, so you are confident at the 95% level, you have to add to the estimator 2.24 divided by the square root of n, or subtract that to get the left one. This 2.24 looks like a magic number, but it's not a magic number. We'll find it out. But with this formula, you get your confidence interval, and we'll see how this works out in a few minutes. So let's say that from 100 trials, you get 43 times A. Then your probability is going to be 0.43. And here I want to show you how this interval, because you see that n is in the denominator here, how much the number of samples that you get influence your confidence on the interval, or not the confidence, but how thick or how thin the interval is. If you have 100 trials, a 95 confidence interval, if you plug the number here with your estimator 0.43, you get the interval between 0.2 and 0.65. So you get around 40 something, 0.40, the width. Now, if you draw 10,000 trials, this guy comes from 0.40 to 0.45, very, very small, very, very close to the real number. So it means that the more data that you have, the more confident you're going to be, or the more close to the accurate value you will be. And this makes sense, right? Because you have more information on what you're drawing, and then it makes sense that your confidence gets higher. Not the confidence, but the interval, sorry, it gets smaller. So it's the same like saying that you will have a distribution like this, then you will have a distribution like this, right? Your confidence is going to be much smaller, the interval, around what you calculate. So let's see how this 224 comes from. At the end, the idea is that you will have the probability that your interval, your parameter, your estimation, P, let's say in this case, between these two borders is going to be equal to something that you want to be, like 95%, right? You want to be that the probability is very high that your parameter is between these two borders, okay? So basically, these two guys, this Rn is your estimation, right? Define our interval, our confidence interval, these two parameters. So what do we do? First, we define, again, epsilon, as a fraction of nothing equal to the value that I said before. And our estimation is our Rn in this case. So P will fluctuate between the estimation minus epsilon and estimation plus epsilon, right? Or it's the same to say that the module of this subtraction is less or equal to epsilon. Remember Chebyshev from, I don't know, 5 weeks ago? That is say that this difference, the probability of this difference to be larger than epsilon is this inequality is less or equal to 1 over this parameter squared times the variance. This is the variance of the sample. Watch out. So you remember that, right? That we did this for the lower the large number. So the variance of the, in this case, sorry, I forgot to say that we are talking about Bernoulli experiment. So it's Bernoulli experiment. Our variance was P times 1 minus P, and since we're talking about the variance of the sample, we have to divide it by n, right? So we have P times 1 minus P over n as our variance of the mean of the sample. We have to see one more thing. What is the highest variance that you could have? You cannot, you are able to calculate that because the higher variance is going to be when both P and 1 minus P is equal to 0.5, right? So when you are just in the middle. And 0.05 times 0.05 is 0.25, right? It's 1/4. So P times 1 minus P is always going to be less or equal to 1/4, okay? This is important because we're going to use it later. Well, this is just to show you what is the maximum of this function. Here, the maximum is in 1/4. So again, let's say that our probability then is that, we already say, and this is equal to 1 minus the probability of this to be larger, because it's 1 minus, it's the complement. This part is the complement of this part, right? So now we have set up like this. If we set up like this, right, it sounds like a Chebyshev inequality, right? So we can say that this is equal, 1 minus that is equal to, is always larger or equal to 1 minus the epsilon squared times the variance. The variance we have calculated here. We put it there. And the epsilon we have defined it here as 224 divided by the square root of n. So we plug it here, and if you plug it here, you have everything that you want because P times 1 minus P is always at least 1/4, right? So you put it here, and you end up with 1 minus 1 divided by 4 times 2.24 squared, which is the magic number of 0.95. So the probability when you use 224 of your estimation to be between this confidence interval is 95%. So what you're saying is your interval, your confidence interval is at the 95%. And that's what is the magic, and the magic number, that's all. So then you can replace this 224 by a variable, and depending whatever you put in mu is your confidence that you will have. For example, if you use the 5 instead of 224, then you will get 99% chances. And 224 is just the square root of 5. Okay, that's where this 324 actually comes from. All right. So, yeah, I guess this is clear now how you do this. Again, you will see that our n play a role again, so this is nothing changed. And there is one more thing. Usually you don't define, or many times you don't define by the maximum probability of 95%, let's say, but you talk about something that is called alpha. You will see in the statistic that we use it more often, and alpha is nothing but this 95, 1 minus 95%. So usually you define by 0.05 instead of saying 95%. Or you say 0.1, or you say 0.001. All right? So this is for you to know that this expression might change in this respect. So to give you an example of how influence that your interval is wider or not wider is basically if you have a data like this, for example, and you have one guy that is screwing your distribution. If you take it the 95%, you will be doing the regression kind of like this, let's say, and then you will exclude this guy because you say this is not erroneous. But if you take a 99%, then you will include that guy. So it's going to be always a trade-off for you to be how big your confidence interval has to be, right? You want to be more inclusive or more accurate. This is up to you, and this is up to your ideas here. All right. So what we do after we explain something theoretical, we do just one. We do an example. So here we have, let's say that we have a variable that is normally distributed, so some mu and some alpha, some variance, and we have defined some interval, right, with some confidence that we want. So we want to find the confidence interval. So what we do? First, you have to calculate your estimate. Your estimate of the normal distribution was the arithmetic mean. We found out that before. And the variance is the variance of the sample. So it's the population variance divided by n. It's always like this. So your mu, now, it will become, now you want to do this in the standard normal distribution, right? You want to standardize your value, remember? Always we do this. So we subtract the mean, and we divide it by the variance, which is the standard deviation, sorry, that is the variance square root. This was our standard deviation, right? This is what we do here. So now we will have for sure a mean of 0, or expected value of 0, and a new variance of 1. This is what you want. So now, second step to calculate your confidence interval is define your gamma. 99%, 95%. Let's say you choose one of those. Depending on what you choose, now you have a standardized normal distribution. What you can do? Use your table. Because your estimation now is going to come on 0, because it's standardized. So your intervals are not going to be the real number, but it's going to be these standard values, and you have to find it out. So this is why we define it here as C and minus C, which is going to be your confidence interval limit now in the standardized shape or curve. So how you do that? You have, this is your interval, right? This is, for example, 95%. The two tails that you have to the other side are going to be 0.25. This is 95. This is going to be 2.5, and this is going to be 2.5, right? So you have to take that into account. So you have to look at C, but you have to look at C not at 0.9. If you are looking about 0. Let's say what we want you to do here. We want you to go, for example, at 95%. You will have to look at the one that is 0.95 in your table, which is 1.645. You have to find out now your intervals. How you do that? You know that your estimation is your standardized version of your values, right? If you multiply by this, you get that this guy now becomes that, and this guy becomes that. Then you can reverse it, right? And then you can add the mean on each curve, and then your estimation will be between these two intervals. And these are your interval of confidence now in the standardized way. The standard deviation, you will have it. The number of samples, you will have it usually. What you have to find is your C, which you have defined it here, okay, from the table. And from that, you basically, is what I show you here is basically the same right here, From that, you will have to contract now your new thing with the values of C. And this CU here is basically what you have there. So basically, to make it simple, you take your values in the real life. You go to the standardized table. You get your standardized border, and then you go back to reality, let's say, and you de-standardize this by multiplying that. Okay? And basically, that's it. Your interval will be 2 times the tails, and it will depend, of course, of n, as we saw before. So let's do a real example to make it this clear what I said before. Let's say that we are measuring a screw, very exciting task. You measure the screw and you say how big they are. And the manufacturers say that, that the variance should be 4 millimeters squared, or one of the measures, okay? Let's test that with a confidence interval of 95%, okay? So we have some data here, 10 points. And we know that we want to be confident on the 95% level. Then we do our calculation, how we do this. So we want to be the probability to be 95%, right? Then we know that it's mirror symmetric, as always, so it's 2 times this. So this is already, we have walk around this again. So now you have the 25% to the right and 25%, 2.5% to the right, 2.5% to the left. So you look at your C for 0.975. You don't look for 0.95, but you have to add your small part here, okay? Because this is what you want to have, right? And then you will get your C, 1.96, and if you have that, you pretty much have everything. You calculate the mean. So one thing is that it has to be normally distributed, right? I didn't say that, but it's important. So the mean of the normal distribution will be the sum of these divided by 10. This is what we do here. The mean is 10 millimeters. Now we have the estimator. Now we construct the confidence interval. So it's basically our C times the variance, in this case, the variance that we get from the manufacturer. Sorry, the variance, no, the standard deviation that we get for the manufacturer, which will be square root of 4, because he say there is a 4 millimeter. And then C, we calculated 2 millimeter, 10 is the number of samples. Our K here is 1 to 24. So our estimation will be the mean plus K and the mean minus K. Mean is 10 always, plus 1.24 minus 1.24. We get a confidence interval of saying that our mu is within 8.76 and 11.24. So a little bit less than 9 and a little bit more than 11. So what we can say, our interval confidence is 2.48 millimeters. Now we have to go back to our data, and if you see, this guy is below 8 something, this guy is above 11, this guy is below 8, this guy is above, below. So most of, already 4 out of 10 fall outside our confidence interval, so we are not that confident of this here, okay? Because our confidence interval say the mean should be, or estimation should be, between 8.76 and 11.24. And 4 out of 10 of our values is already outside our confidence interval. So we are not very confident, at least at the 95%. If we go to the 99%, maybe we cover more data here. So this is a way of studying this. You will see that this is very important for the statistic later to see if two distributions are different or not. You will see how this plays a role. So we are screwed, right? Let's say. So then the next thing is, let's say that you have your standard deviation or your variance. You know the confidence interval that you want to be at the confidence level, sorry. And you know that the interval length is 2. So then the next question could be, how many samples you need to get these parameters? You can already think that if our interval confidence is defined like this, the only thing that you have to do is to find C, and you have to solve for n. Nothing really crazy here. So if you solve for n, this is your equation, and then you just need to find C. C to the 99% is the same story than before. You have a confidence interval of 99%, you will have 0.05% or 0.5% to the right and to the left. So when you go to look at C, you don't look for 99, you look for 99.5. And then you will get another number, 2.57. We again assuming that it's a normal distribution. I hope at some point, okay, I say it, I didn't say it, but it's a normal distribution. So with the equation, if you plug your C here, then you get 664 samples, what you need to get your interval confidence. All right, so that's it for today. I hope you learning something else today. So there was another method to estimate it, and now we have a method to see how good our estimation is. Next week we continue, but for now, that is all. Thank you so much.